So this is kind of introduction to the climate system and climate change science. This might at times seem like, going back to school, some of the kind of background science, but hopefully you'll get at least something out of some of this. So just start from scratch, like as you would in the first day of your undergrad course. So what is weather? What's climate variability? What's climate and what's climate change? So weather is basically the current atmospheric conditions at a particular place and time, or a few hours to a few days. That's the weather, and we kind of get a weather report every night. That's details that kind of information. So climate variability is natural variations in the climate that occurs between weeks, months, seasons and years and longer. So there's also climate variability at the scales of centuries and thousands of years. Think of ice ages, etc. But usually within most kind of contexts, we primarily focus on things like months and seasons and years in terms of climate variability. What is the climate and how is it different from weather? So the climate is the average pattern of weather and other conditions for a particular place over decades. So for example, over 30 years, you can generate some statistics. That's a climatology, or a description of the climate. It's also, the climate is also all of the different components of the climate system and their interactions. So this is the oceans, the atmosphere, the ice, the land surface, humans too, and how they kind of interact and create these conditions that we experience at each place. And climate change is the long-term trends in the climate over decades to centuries. So we can talk about the change in the averages, talk about the average change in statistics. We can also talk about the change in the likelihood of extreme events. So this is how we can relate weather and weather extremes to the climate. You can say how likely a particular extreme was, or in a given climate and compared to a different climate. So here's a graph of say temperature at a particular place. Doesn't really matter what it is. This is the kind of thing you would see if you took measurements every day and plotted it over 5 years. You'd see a lot of ups and downs, a lot of wiggles, and then if you drew a kind of running mean through that, you'd get a definite annual cycle in most places. Some places have got a very small annual cycle, and you'd have differences from year to year. You'd have differences between seasons in the different years, etc. So this is kind of some of the kind of statistics you can generate for about climate variability. What influences our climate variability? Well, everyone here should be familiar with El Niños, La Niñas. El Niño, southern oscillation, kind of oscillation in the Pacific that can have big effects on our seasonal climate. We just kind of have been kind of going through a La Niña summer, so that's tended to create cooler, cloudier, wetter summers than El Niños. These relationships are always, loose. Like it's not like set in stone what you get, but they kind of push things one way or the other way to their tendency. But there's a lot of other influences that are important. So the Indian Ocean is getting more widely known these days, and particularly an oscillation there. The Indian Ocean Dipole, or IOD, has really important effects all around the Indian Basin, including in Africa, but also in Australia. That can have a big influence on our seasonal climate. There's the Southern Annular Mode. That is a kind of an oscillation around the Southern Ocean, which affects especially the weather systems affecting Southern Australia, but also has kind of related effects in other places. And there's a lot of other kind of features and oscillations and so on that are called drivers of our weather variability and climate variability. And these have different effects in different seasons. For example, El Niños come along at a particular time of year and affect our spring and summer weather, and then they kind of go away. So some of these have got a real seasonal aspect to them. So when we start gathering enough data, we can also then look at not only climate variability and interannual variability. We can start looking at longer term trends, and you might see something like this with an upward trend over the 50 years of record, and you can start to say, okay, is this a notable trend, and then what's causing it, and this is where we start talking about climate change and climate change scales. So as I mentioned, climate and climate change is a function of the climate system and all its influences. And here's a little kind of cartoon or schematic of the different components. So big one, of course, is the sun and the solar output that we receive. some noise there. Yeah, jump in if I'm kind of going off track. Otherwise, yeah, if you could kind of mute, that'd be great. And yeah, a lot of different gases involved in the atmosphere that are relevant here in terms of the greenhouse effect and other effects. There's interactions between the ocean, ice, land, human systems, hydrosphere, volcanoes have a short-term effect on the climate. And of course, change in the composition of the atmosphere is now known to be a big driver over climate change scales, as well as things like changes to land surface and land use can affect the regional and global climate and other effects. Of course, a very notable one that's become rightly known as a very important driver of our recent and climate and likely into the future is, of course, the greenhouse effect. And this is back to high school science. Hopefully this is kind of in everyone's kind of background. The sunlight reaching the Earth is absorbed, the Earth re-emits heat or long wave radiation, and then some of that is then absorbed and then re-radiated from gases in the atmosphere, which is kind of forms a kind of a heating blanket-like effect, and this is called the natural greenhouse effect. And then with increased greenhouse gases in the atmosphere, then you get an enhanced greenhouse effect, and that leads to a rise in temperatures at the surface and a cooling of temperatures high in the atmosphere as that radiation balance is altered. How far back does this go? Like sometimes, your cranky uncle might say, oh, it's all very fashionable, this new greenhouse effect and, climate change bizzo. Well, I mean, the earliest kind of theories that are relevant to the greenhouse effect have been known for well over, 100 years. So John Tyndall was known as kind of the person who published the first set of experiments about the effect of CO2 in air. However, this is kind of overlooking the groundbreaking work published prior to him by Eunice Foote, whose study Circumstances Affecting the Heat of the Sun's Rays in 1856 actually predates John Tyndall, and she's now getting the recognition she deserves. It just wasn't, communication wasn't that great at that time, and so she was just overlooked, unfortunately. But yeah, these lab experiments gave very clear results even back then. Our next part of the story is putting together that effect with to create a theory about what effect it would have on the climate. And 1896, this Arrhenius paper is very famous now on the influence of carbonic acid in the air upon the temperature of the ground, 1896. And he according to his calculations, a doubling of CO2 in the atmosphere would lead to 5 to 6 degrees warming of the global surface temperature. This is probably a little bit high given our knowledge to date, but it was right in the right ballpark. So it was pretty well established even back that far. Another really important part of the history here is Guy Callendar, which is a good name for earth sciences, in 1938 looked at the trend in temperatures at 140 weather stations, which he took as a measure of the broad scale change, and worked out that it was consistent with what was known then as the CO2 effect. And you can see one of his original hand-drawn graphs there at the bottom, looking at the departure from normal of the trend in there averaged over those 147 stations, and he calls that the CO2 effect. At the time, he thought, oh, this is all for the good. This is great. This will delay the return of deadly glaciers. But perhaps he was, really visionary in terms of looking for this, but perhaps a little bit short-sighted and thinking about the possible downside of this. So another aspect of looking back at the past is, well, with the Earth's history, and here is a plot. You've probably seen something similar to this a few times, but just to go through it briefly, this is from State of the Climate 2020 in Australia. The panel on the right shows carbon dioxide concentrations in the air measured directly from stations. Let's see if we move this over here. There we are. Including in the red line, and measured from ice core measurements in the light blue line. This is looking back the last 2,000 years. It shows a very stable period and then a very rapid rise kind of after industrialization really gets going. And in 2019, the carbon dioxide was 407 ppm measured at Cape Grim, which I know Jill will be very familiar with. And carbon dioxide equivalent was up over 500 parts per million. That's all the different greenhouse gases put together and converted to equivalent of carbon dioxide. And currently is rising at 2 to 3 parts per million per year. That's the carbon dioxide. Putting that in a longer term context, we can go back at least 800,000 years using direct measurements from air trapped in ice in Antarctica, and we can put that in that longer term context. And you can see ice ages coming and going, and then just only the very recent period where there's been any concentrations above 300 parts per million. And that's also likely back at least 2 million years that CO2 has never been this high. And we know also in the past that these the CO2 concentration in the air has been tightly coupled to the global average temperature. We know this through looking both at the concentration of carbon dioxide in the air bubbles in ice and also the chemistry of the ice as well, which gives you a kind of a proxy for temperature. And you can see how these two things closely line up over that history. All right, so moving to more recent times, here's a version of a very famous graph now, the global mean surface temperature change relative to an early period. We're taken as kind of a proxy for pre-industrial, 1850 to 1900. Using different data sets that kind of try and get at what that value is from the data available, and they strongly agree. And we're currently sitting at about 1.1 degrees above the 1850 to 1900 baseline. And this is taken as a measure of a progress towards things like the Paris Agreement limits, so to keep warming below, well below 2 degrees and aim to keep it below 1.5 degrees. We're already at 1.1. So it just shows you how far along the road we are there. Of course, there's variability in the global average surface temperature, but also there's different eras where there's different trends. We expect short-term differences and departures from we don't expect it to be smooth because there's processes that kind of come along. But overall, the change is extremely clear. Of course, climate isn't just about global temperature, it's also about other aspects of the climate. So sea level, we've now hit kind of a bad milestone. Since 1880, it's likely the global average sea level has risen by around 25 centimetres. It varies, the rate is different, or the change is different in different places around the world, and it varies around the Australian coast. Also, the coast in different places has a different vulnerability to sea level rise. So some places are sandy shores, for example, and they can erode compared to rocky shores that don't. So the effect of climate change is different in different places, and also the rate of climate change is different in different places. And not only has it increased over the last 140 years, the rate has accelerated. So you can see a slight upward curve to this line, and it's currently rising at 3 centimetres per decade as the global average. And the two different colours there are the older kind of tide gauge measurements and the more recent satellite altimetry measurements. And there's some differences, but they broadly agree on the trends over that recent period. Looking more locally, so Australia has warmed by about 1.44 degrees since 1910, since we've got reliable records from weather stations. 2019 was Australia's hottest year on record, and it was about 1.5 degrees above the 1961 to 1990 climatology, which is pretty extraordinary considering no year before 1970 had a value above half a degree above that baseline climatology. And you can see there's been a very few years since 1970 that have actually had close to or cooler than that climate average, so that climatology. So the trend is very clear in Australia, but you'll also notice that there's more variability year to year at the Australian scale compared to the global scale. This is kind of a signal to noise issue. And when you go down to a particular state, for example, New South Wales, you can see the variability can be larger there as well. So you can have more ups and downs as you go along. You have more eras where there's kind of an unclear trend. But even at this kind of state level and sub-state level, you can still see the overall long-term trend is there. This one's New South Wales, but it's a similar story for any kind of state average. Of course, average warming of the climate and leads to a change in the incidence of extreme events. So an increase in the occurrence of hot extremes and a decrease in cold extremes. This is a particular measure given by the Bureau of Meteorology, which is number of hot nights. So nights with a minimum temperature above 20 degrees. And you can see a steady change there for an increase in the number of hot nights, and including years with unprecedented numbers compared to the early part of the history. And you'll see a similar but opposite change in a lot of cold extremes, decreases in cold nights, cold days, etc. in many places. And the number of new records in terms of hot extremes, really outnumbers the number of new records being set in terms of cold extremes. So that's a shifting odds kind of idea. Climate change also affects atmospheric circulation, other kind of other rainfall processes, and so can affect average rainfall that we experience. This is again from State of the Climate 2020, looking at the average rainfall during the cool, wet season in southern Australia over the last 20 years. And much of southern Australia is coloured orange to red in the below average, down to lowest on record in terms of 20-year periods in the whole record. Some areas, some regional exceptions to that, like Western Tasmania. But on the whole, it's seen very dry conditions in the last 20 years compared to the longer term record. You can also see that in the time series of rainfall in southwest Western Australia, for example, has seen a steady decrease in rainfall over the last 100 years, and very few years in the recent times with rainfall that's very wet, kind of the recharging kind of years. And there's been a significant decrease in rainfall, you can see in the time series in Southeast Australia since the 1990s, and fewer years with that really wet conditions in Southeast as well. I should mention Southwest Western Australia has got a very strong and well-studied climate change signal. There's a strong effect of human influence on driving that climate change signal in Southwest. There's some evidence that the Southeast is been driven by climate change as well, although of course natural climate variability plays a role in both of these cases. Looking at the Northern Australian wet season or warm season, there's kind of the opposite story. It's wetter in summer there than in winter, or what they call the wet season. And there's seen an increase in rainfall in the last 20 years compared to the long-term average. This is a complex kind of set of drivers leading to this, like there's natural climate variability. There's also possibly an influence from aerosol pollution from Asia. There's also possibly a climate change signal in that, but it's much less clear and kind of more complex. But just, the last 20 years have been wet compared to the previous period. That's definitely the case. Looking at the future, this is the kind of high-level statements that get put out in products like State of the Climate. So high-level, headline takeaways for people to kind of to remember are things like some of these recent trends are really projected to continue with climate variability as well. So global temperature to rise, sea level to continue rising, marine heat waves, which are periods when the ocean temperature is above normal, to become more frequent and more intense, warmer with more heat waves, fewer cool days in most places. Cool season rainfall to continue declining in southwest Western Australia and likely in southeastern Australia, but kind of conversely, heavy rainfalls to become more intense due to a warmer atmosphere and other influences, and really importantly, a longer fire season and more dangerous fire weather days, which is of a particular interest in terms of hazard management and risk management in Australia. There's also some which are kind of cutting edge topics like tropical cyclones. There's a lot of research on this, but it's less clear and it's more complicated. But the current assessment of the evidence suggests that overall in the long term, there's going to be fewer tropical cyclones, total number, but a greater proportion of those to be high intensity cyclones. So, and also the impact of tropical cyclones to increase because they can bring more rainfall, drop more rainfall. They also will be occurring on top of a higher sea level. So coastal inundation from tropical cyclones is likely to be higher. So yeah, kind of complex, more complex story there, but some good evidence for increased impacts overall. And here's some sources that was drew on to do this section. Definitely check out State of the Climate 2020 from last year. There's also some other links there, some good stuff on the Bureau website to click around, not just in the weather bit, but the land and food area, the climate guides, for example, the hydrology sections, etc. And there's some other kind of resources there too. So how about we stop there? I've no idea whether I went through that too fast or too slow, but should we stop and do some Q&A? What do you think, Beck?
Yep, that'd be great. There's nothing in the chat so far, so if anyone wants to pipe up with a question, perhaps that's the first step.
Yeah, so maybe I did go through too fast, or maybe it was too basic for everyone here. Everyone goes, oh, I've known this since high school. But hopefully there's a few bits and pieces in there that you maybe hadn't heard before, or at the very latest, maybe data on some of these things.
Yes, hi, Michael. I have a question. My name's Chris.
Yeah.
I'm a network planning engineer at the Australian Energy Market Operator. I just have a question about vegetation. It's sort of it's a big thing for transmission planning engineers to consider. And I'm wondering if there is any trends or patterns in vegetation sort of growing back quicker or anything like that with the increased CO2 in the atmosphere, or just anything in that space at all that might ultimately influence the occurrence of fire danger to the transmission network.
Yeah, that's a really good question, a bit of a curly one because it is kind of complicated, but I'll try and be fair and balanced on this topic. So yeah, overall fire danger is, of course, not just weather, it's also the vegetation. Effects on vegetation are also kind of complicated because, as you say, there's the CO2 effect, CO2 fertilization of plants. That can increase their water use efficiency, so they can grow better because they don't have to open their stomata so much, so they can actually use water more efficiently. So in some ways, it kind of suggests that there's going to be a boost to some types of vegetation, but it's kind of more complicated than that because there's a difference between different types of plants and how they respond to that CO2 effect. Then there's also the change in the physical climate that the vegetation grows in. So hotter temperatures, changes to rainfall as well also affect plant growth as well as the CO2 effect. And what happens, and then there's the fire itself. Obviously, if you get more frequent fires, that changes the vegetation type and structure as well. So it's one of those areas which is really complicated and kind of can be, and people do sophisticated modeling of these different factors to kind of see how it all plays out. Past trends, there's been a notable trend towards kind of greening of the land, so a bit more what they call, what's it called, leaf index or vegetation index in most places, partly likely due to this CO2 effect already, but that's not entirely clear. And it's also not clear whether that will continue and whether these other factors will kind of counteract it, etc. So yeah, vegetation is a tricky one. But it's really important to get better at because it not only affects fire, but it also affects things like evaporation, or evapotranspiration, I should say. So the total water loss off the land is also what goes through plants. So yeah, hopefully that's helpful.
Yeah, absolutely. Thanks for that. I think sort of consistent with everything else that's quite complicated with this sort of work. So yeah.
Yeah, no worries.
Anyone else? Oh, there's one comment in the chat just saying that some of the introductory info was basic, but the later information was useful.
Okay, great.
I'll have one more question as well. This is Luke Fuller from, same as Chris from EMO.
Hi, Luke.
So one of the other aspects we struggle with as well is things like extreme wind. For example, South Australia, we had those transmission lines blow down, lead to the blackout, and also last year we had some big transmission lines blow down in Victoria. And so when we ever try to look at justifying building these lines stronger or things like that, we've always just asked about, well, was this a 1 in 20-year event? Was it a 1 in 30-year event? And so that's one of the areas we always struggle with having good numbers with. Is there any progress to looking at aspects like that?
Yeah, so I mean, all the interesting topics are also complicated topics, aren't they? So wind is one of those ones as well. So, I mean, extreme winds kind of vary from place to place because they're kind of brought by different types of weather patterns. So, of course, you know, tropical cyclones have got extreme winds with them, and that's relevant to Northern Australia, but not relevant to Southern Australia. And, you know, extreme winds come from extreme storms that affect Southern Australia, including, you know, intense lows and various things. And in many cases, we need to look specifically at the things that bring that extreme wind, because there's no general rule of thumb that globally, unlike, say, temperature. Mean temperature is going to go up almost everywhere. It's pretty clear cut. Extreme wind will vary from place to place very strongly. And there's some good work on some types of systems that bring extreme wind, and there's poor work on others, unfortunately, and all of it is less confident than some other aspects of climate change, just because of the nature of, you know, what is the flow and effect of a warmer climate on the intensity of extreme storms is a harder question than some of these other topics. So, yeah, again, sorry, I'm kind of not giving you a clear answer, but yeah.
Hi, Michael. Jason Lindley from Essential Energy.
Hi, Jason.
Yeah, just following on from Luke's comment around wind, and I understand that it's complicated. But I guess the transmission view might be slightly different from a distribution view, where they may be assessing a particular line, from point A to point B, and considering the very localized changes to whether they could expect. I guess we are, interested in that sort of probably a broader scale. Are we expecting that cyclonic wind zone to shift further south? So currently in our design standard for overhead lines at Corindi, we say, well, we apply cyclonic winds above north of Corindi and non-cyclonic winds below Corindi. So I guess that's, are we understanding at a level or at a position where we're understanding those changes yet?
So just for my reference, where's Corindi exactly?
It's on the north coast of New South Wales.
Yep. So, and you're mainly talking about the extreme winds from tropical cyclones?
Well, tropical cyclones and...
Or ex-tropical cyclones?
Ex-tropical cyclones and east coast lows as well.
East coast lows, yeah. Yeah, so, I mean, there's raging debates about a few of these things and different lines of evidence to bring together. But the kind of the assessment of all those different lines of evidence kind of comes together to produce statements like, a southern movement of the extent of where tropical cyclones can make landfall is more likely than unlikely, which is, I know, not as certain as we would like, but when there's evidence that the tropical zone will expand and tropical cyclones will be able to make landfall further south than they do now, but there's also a lot of decade to decade variability and some other evidence that kind of, sheds a little, throws a little bit of caution on that. East Coast lows, there's also some good work on that, and there's some things which are more clear than others. For example, the projected changes in winter are more certain than in summer, and in winter, decrease in total number in the long run is I think the projection. But how about, this isn't my area of real expertise, so how about I put you in touch with or send you some material on projections specifically for tropical cyclones and East Coast lows produced either through this project or related projects? Would that be helpful?
That certainly would. Thank you, Michael.
Yep. No worries.